Hello student, good morning. I am Dr. Ajay Kumar Sinha, Professor of Chemistry. Today I will continue from the last class. Last class I was discussing geometrical isomerism. Only in that two more I will discuss. It's a small but in examination question is asked. That is facial isomer and other is meridional isomer. What is this facial? First I will tell. Here that is another type of geometrical isomerism. This is another type of geometrical isomerism. Occurs in octahedral coordination entities of the type Ma3B3. Ma3B3. Actually, I told you heteroleptic and homoleptic two types are there. Heteroleptic means different donor. If different donors are there in isomerism, that in a complex compound, if donors are same, ligands are same, then that is called homo. And if it is different ligands are there, different type of ligands are there, that is called heteroleptic. Then here I am talking about this only Ma3B3. It is heteroleptic. Then this is another type of geometrical isomerism, occurs in octahedral. Ma3B3. M is central metal ion, a small a and a small b. A3B3, that is the ligands, different ligands. Like example, cobalt NH3 whole 2 and NO2 whole 3. Cobalt NH3 whole 3, NO2 whole 3. This is under the square bracket. If three donor, here two type of donors are there, ammonia, another donor is NO2. Both are 3, total 6. Then if three donor atoms are of the same ligand, occupying adjacent positions at the corners of an octahedral face, we have the facial isomer. In that situation, we can tell we have facial isomer. Again you listen. If three donor atoms of the same ligands occupy adjacent position at the corners of an octahedral face, then that time we can tell we have facial isomer. FAC shortcut, FAC, facial isomers. Okay, means there will be 6 points will be there in octahedral. In case of octahedral means 6 ligands will be there. If three ligands are same and they are occupying adjacent position, close, continuously 3 ligands are there, same type of ligands, then that time facial isomers occurs. Okay, we obtain facial isomer, FAC shortcut. Same, for example, now you can see that cobalt NH3 whole 3, NO2 whole 3, then all 3 NH3 are in the you can say adjacent position at the corners of octahedral. Means out of 6, 3 ligands are adjacent to each other. 3 ligands continuously, like NH3, 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 all 3 are close, and 3NO2 are again close. Means NH3 is separate, all 3 are separate, close means adjacent to each other, and 3NO2 are opposite. All 3 NO2 are opposite. Then this is called face, just like a face. That's why it is called facial. You can say isomers. Now another type is meridian. Meridian. Only that basis. Meridional isomer, in shortcut MER. Meridional, MERI, meridian. From that it came meridional isomer. Then how you will get this type of isomer? Then when positions are around the meridian of the octahedron, from this word meridian only meridional isomer came. Then how you will get this meridional isomer? Then when the positions are around the meridian of the octahedron. In that case, in facial you have seen 3 were one side, means adjacent to each other, and other NO2 was other side, each adjacent position on a this things octahedral corner. All were on a octahedral corner, but only thing was that 3 were adjacent to each other, and NO2 was, all NO2 was another side adjacent to each other. Okay, that time it was called facial, FAC. Now same way, when the positions are around the meridian means middle. Meridian means just like you can say middle only. You can, in broader sense, we can tell middle only. When the positions are around the meridian of the octahedral, in that situation we get the meridional isomer, MER. Then here example I am telling you, cobalt. Same this formula is the same. Here 6 are there, but now all are mixed. As for example, now out of 3 NH2, 2 are close, NH2, and third NH3, 2 are close, and third one NH3 is opposite. Means 2 NH3 are opposite, and third NH3 are 2 out of 3, 2 are close, and third one is opposite. You can understand like that. Out of 3 NH3, 2 NH3 are close, adjacent, and third one is opposite, just like a straight line, one above the cobalt, other below the cobalt. Like that way, 3 NO2 are there, then 2 NO2 are close, adjacent, and third NO2 is opposite means far. Just like one is the above NO2 and other is below the cobalt. Means cobalt is in the middle. Then one NO2 is above the cobalt, other is below the cobalt. Means you can tell between the 2 NO2 NH3 is coming. Between the 2 NO2 NH3 is coming. Correct? Then this is just like a meridian position, meridian of the octahedron. Total 6 are there, total 6, but they are differing in arrangement. Then here you can understand that this facial and meridional isomers both exist in the case of Ma3B3. Means in octahedral coordination entities these two occurs, these two isomers, facial isomer and meridional isomers. Okay. Now this one question is asked, why is geometrical isomerism is not possible in tetrahedral complexes having two different types of unidented ligands. Again listen, why is geometrical isomerism is not possible in tetrahedral complexes having two different types of unidented ligands coordinated with the central metal ion? Then now I am telling you explanation. Tetrahedral complexes do not show geometrical isomerism. Why? Because the relative position of the unidented ligands, attached to the central metal ion are the same with respect to each other. This is the main reason. Again I am telling you, tetrahedral complexes do not show geometrical isomerism because the relative position of the unidented ligands, two types of ligands generally will be there. Then unidented, both are unidented ligands attached to the central metal atom are the same with respect to each other. Relative positions are same. Okay, this is the main reason. Relative position of the unidented ligands attached to the central atom are the same with respect to each other. Now I am going to discuss optical isomerism. Optical isomerism. Optical isomers are mirror images that cannot be superimposed on one another. These are called as enantiomers. First you understand this, I told you cannot be superimposed on one another. Optical isomers are mirror images that cannot be superimposed on one another. Now mirror image you can understand like that. Suppose your left hand is the mirror image of the right hand. Left hand and right hand, just to see that both are the example of mirror image. Means one is the image of other. Left hand is the image for right hand. Right hand is the image for left hand. But see what is the difference in both hand. This is the important things. Then both hand can't be superimposed. Correct? Both hand can't be, that is the mirror image. Both are mirror image. Left hand is the mirror image for right hand. Then both can't be, I can say, superimposed. Correct? Both have 5 fingers, all things are same. Arrangement is also 5 fingers are arranged in a proper way. But just if you will want to image, just like your face, if you will see your face in the mirror, then what will happen? That will be opposite to you. Your face only, but it is opposite. You can't keep one another. means superimposed one on one another. You can't keep can't be superimposed on one another. Right hand fingers and left hand fingers, you can't keep that thumb. In one case, thumb will come to the smallest finger. If you want to keep, then thumb will come to the smallest, and a small will come to the thumb, both hand. Correct? Both can't be in the same direction. In the same direction, you can't. It will be not superimposed. Okay, in opposite direction it can be superimposed, just like your face in the mirror. If you go close, it can touch nose to nose, but in the same direction, it is not possible. Okay. Then here finger you understand best. Example that it can't be superimposed. This is the example of mirror image. And direction wise change will be in that direction. Okay. Then now optical isomers, I was discussing. Optical isomers are mirror image that cannot be superimposed on one another. This is the main condition. And after that, these two type of isomers. These isomers are called as enantiomers. This type of isomers which can't be superimposed, that is called enantiomers. Question is asked, what is the enantiomers? Then enantiomers are mirror image that cannot be superimposed. These isomers are called enantiomers. 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 These molecules or ions that cannot be superimposed are called chiral. Okay, and what we will do about these molecules? These molecules can't be superimposed. Then mirror image, two images there now, one original, other is a mirror image. Then you can tell two isomer, then each isomer, two are there. Then each will, what you will call for each isomer. Then the molecules or ions that cannot be superimposed. The molecules or ions that cannot be superimposed are called chiral. 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 Remember, two terms I told you, enantiomers. Then both are called enantiomers. First things, and second, molecules. What we will call for the molecules? Then the molecules or ions that cannot be superimposed, that molecules or that ions are called chiral. Okay. The two forms are called, again you tell third term, important term, all are important only. The two forms are called dextro, small d, DEXTRO, dextro, D, small d, and labo, LAEVO, labo, small l. Depending upon the direction, they rotate the plane of polarized light in a polarimeter. One instrument is there in that experiment, polarimeter experiment. D means and L means. D rotates actually when light is passed. Suppose in polarimeter experiment, what happens, there will be one glass tube. In that glass tube, in polarimeter, one tube will be there. In that tube, you can put the solution. Suppose sugar solution you have taken. Sugar solution, maybe glucose, fructose, anything, any solution you have taken, and you just kept inside the polarimeter. And now if light will be passed, one this will be there, this in polarimeters, that one lens will be there inside, actually glass will be there. Through that glass you have to pass the light. You have to pass the light and through that glass, correct? And due to this light, after passing the light, what will happen, that in solution, suppose any sugar, like maybe glucose, maybe fructose, any one you can consider, then this light, this sugar molecule have capacity to rotate the light, either in right direction, clockwise or anti-clockwise, only two ways. Okay, it can rotate the light in you can say left direction, right direction, or left direction. You remember, this molecules has capacity to rotate the light, direction of light. Light was passing, coming to the solution, correct? Then in solution, molecules are there, sugar molecules are there, maybe glucose as for example. Then this glucose can rotate the light either in right direction or left direction, correct? Then if you will take another solution of fructose, then again it can rotate the light. Okay, like that way maltose you can take, so many solution you can take, then they can rotate the light in different direction. Okay, either left or right. Then if rotates, if we can say these molecules rotate the light in right direction, then it is called D isomer, a small d. And if rotates to left, then L means left, L means labo. Remember it, LAEBO, labo. If molecules rotates the light to the left, then it is called labo. Remember, L means labo, L means left. Okay, and then the rest, another is this dextro. Dextro means D rotates to the right direction. If rotates to the right direction, then it is D. D means dextro, and L means labo. Okay, the optical isomerism is common in octahedral complexes. Again, I am telling you that the two forms, I am talking about the optical isomers. Okay, the two forms are called dextro and labo. DEXTRO. Dextro means D, a small d. It is represented by a small d, and labo, LAEBO, labo, a small l. The two isomers, the two forms are called dextro and labo, depending upon the direction they rotate the plane of polarized light. What is actually polarized light? What is the meaning of polarized light in a polarimeter? Actually, you should understand any light, ordinary light, it vibrates in all direction. But due to some, you can say, I can tell Nichols prism. Directly I am telling you exact. If due to some means here Nichols prism, if you pass the light through Nichols prism, then it will cut other direction light. Only it will send only light only in one direction. In the beginning it was vibrating in all direction, but by some means here means Nichols prism. If you will pass light through the Nichols prism, NICLOSM, Nichols prism, then it will pass the light only in one direction, monodirection. Then that type of light is called polarized light. And in polarimeter, only this type of light is used. And in that tube which you are keeping inside the polarimeter, and light is passing through, in this plane polarized light is passing through this solution via glass. Okay, in that tube. In the tube solution is there, in solution molecule is there, glucose, fructose, anything, any one solution you can consider. Then that can rotate the light either right direction or left direction. Right direction, if it is rotating, that is called dextro, D, small d. If it is rotating left, then lavo, means a small l. Okay, then these two forms are called dextro and lavo, depending upon the direction they rotate the plane of polarized light in a polarimeter, and that tube is called polarimeter tube. Optical isomerism is common in octahedral complexes involving di-dented ligand. Generally, di-dented means two atoms will be there, they can donate the electron. Di-dented ligands will be di-dented means in that molecules two atoms will be there which can donate the pair of electron, lone pair of electron or a electron. You can tell in the symbol, if charge is there, then electron. In the same ligand, two atoms can donate. Okay, that is a di-dented. Then here example I am telling you, optical isomers D and L of cobalt En whole 3. Cobalt En whole 3. En means ethane 1,2 diene. Ethane 1,2 diene. Okay, then ethane 1,2 diamine. Ethane 1,2 diamine. Then diamine means two amine is there, means N is there. NH2 is amine. Then N has lone pair of electron, hence it can donate. Then one En, two electron can be, two N can donate the electron. That's why it is called di-dented. Di-dented. Then here I am telling that thing, that I am telling about that complex cobalt En whole 3, outside 3 plus, because cobalt is oxidation state 3 plus, but this ethane 1,2 diamine is neutral, no charge, but they have, nitrogen have lone pair of electron, they can donate. Then here 3 En whole 3 is there, then 2 into 3, 6 bond it can make. 6 total bond will be 6, means octahedral. Then now here what will happen, I am telling you that one isomer means mirror image I am talking about, that these 3 En will be in 3 direction. 2 En will be just like it will be arranged like that way, all will be roughly, you can tell, equal angles. 180 is then 60 you can consider. All are making difference of 60 degree. Okay, then each ligand, each En will make 2 bond. Okay, each ligand will make 2 bond, di-dented ligand. Then suppose one ligand is, actually I told you this thing, the 3 representation of bond. Three type of representation is there. One will be dark black, okay, and one will be dotted dot, and one will be ordinary line. Then it has three meaning. It will tell, all three will tell about the direction. Then in a simple way, ordinary way, you can understand. If bounds are on the plane, then it will be, you can show by normal bonding line. If bounds are on the plane. If a bond is upside, above, it is not on the paper, out of paper, upside suppose, then that will be shown by dark width. From the, it will increase from 0.2, it will just, the widthness will increase little, not more. Dark, completely dark will be there. Then it means it is going out of paper, up direction. Similarly, if it is going down, it is not on the paper, down the paper, then that is a, we can represent it as a dot. Okay. Then actually any molecules, if you will think in a space, then you will, this all thing concept will come. One will be up, other will be down, and some molecules will be in the one plane. Just like they can be on the paper. Some may be above the paper, some may be down the paper. Correct? Then every time actually you should think like that, then it is very good in understanding the molecules, arrangement of atoms or molecules in a space, right direction you can understand. Then here I was talking about 3 En is there. Each En will make two bond. Then suppose all are at equal distance, 60 you can consider. Okay, 360s are there, na? Equal distance, total 180, 360s are there. Then now you can consider 120, equal distance, all are supposed at equal distance. Okay, then now this is the one form. Then suppose now out of 3 ligand having two, all are this two bond all can make. Then suppose one En is in the back and other two in the front. Correct? Other two in the front and one is the back. Suppose this is the dextro, D means you can write like this way. Always you should write the, in bracket you write all complex and you write in the bracket. Then here cobalt you write in the middle, back side of cobalt you write one En, what you write En, and from that two bond is making. Two bond, then two bond, how will you show the two bond? Both bonds are attached to the cobalt, how will you show? Then simple one example I am telling you, it's a size will be, bond size, but empty you consider, just like these things, onion, full onion you are taking, a full onion size, from one point upside, both side, up will be, then again it will come to the, means swelling will be there, just like and after that and the beginning end point will be there, it will go up, again it will come down, both side, down also, upside also. Then that type of shape you can write for the bond. Okay, that from the En one you can take slightly like a curve, as curve go up, again you bring down, one bond like that way. Another bond you can write starting from En, go down curve down, and again you come little up, and it should make a bond with cobalt. It will look like a onion size shape. Okay, like that way, empty onion, you can say shape will be like that only. Then En is making 2 bond with cobalt. Then like that way, other 2 also you can consider. Okay, now like that way, this 2 in the front, 1 back side, that is the dextro, and it has 3 plus, complex has 3 plus. Then now labo, how will you show? Other if you will keep this dextro, suppose dextro is there, and in the middle you keep mirror, just like you are standing before the mirror, then you will feel that inside the mirror face is there. Your image is inside the mirror, you will think like that. Then same way, 1 molecule you have taken, dextro, and suppose now mirror you have kept, and then what will you see in the mirror? Just like your face, this molecule also, it will reverse. Then now you will feel that now which was back, now it is in the, you can say front. Means there left, you can understand like that, left hand is right hand. Left hand and right hand situation will be there. Then after this dextro, suppose you are keeping in the front of mirror, 1 mirror sign you can write, dot, you can write, that will show the mirror. Then after that, what you will find that what was the 2 in the beginning, 2 En was in the beginning, that will look like that is just in front of them. It will make a diagram in front of them, correct, in front of them, and which was back, that will go back side only, that will go to the back side, just like your face. Very good. Our left hand you put on the mirror, then it will look like a right hand. Okay, then same situations are there. What was the front 2, that will be in the front, and what was the back side, it will go to the back side, correct. Then now both can't be superimposed, because front is front, 2 are okay, but they will also not superimpose, they can't superimpose, just like left hand and right hand you can't superimpose. Okay, thumb will go to the smallest, in the front of a smallest. Again for the other hand, thumb will come to the another hand, smallest finger. Means right hand thumb will come to the left hand smallest finger, and left hand thumb will come to the right hand smallest finger. They can't be superimposed, and that situation is there, and that is called labo. Then you can make the diagram very easily. Like that way, this I told about the when this cobalt En whole 3, cobalt En whole 3 for this complex ion, I have told you, it was having 3 positive charge. Now another example I am telling you, platinum Cl2 En whole 2. Platinum is the central metal ion, P2Cl2 En whole 2, and outside 2 plus is there, charge is 2 plus. Then now here what will happen, 2 chlorine atoms are there and 2 En whole 2 is there. Then how will you represent here, dextro and labo? Then platinum you can write in the central, and after that 2 Cl are there. Then you can make 2 bonds, Cl, they are making bond with platinum. Now 2En is there. Then now 2En, again you can make any way you can make the En. Representation will be same, just like onion representation. It start from the one end, other in the swelling will be there in the middle, again it will come to the both end will meet. It appearance will be like that. Both bond you can start writing like this, because two bond it will overlap to each other if you straight you will write, and better making some distance, then you can make like a curve. Take a start from the one point, take it up and slowly bring down to the platinum, and again another bond, again you start down, go down, curve will go down, and again it will come slowly and it will meet to the platinum. Okay, then 2 Cl you have written and 2 En you have written. Now again you think platinum is back side, and Cl is in the both Cl in the front, and En is one En is also in the front. Then mirror image if you will see, suppose in the middle mirror is there, between the two isomer dextro and labo you consider mirror is there, dot you can write for representation purpose. Then here again what you will see, that 2 Cl was in the front and 1 En was in the front. Then in the mirror again you will see both are in the front only, both are in the front. But Cl first and second, suppose Cl 2 Cl was there, now first and second Cl, then what you will think, second Cl is coming first, second Cl will look like first, okay, and first Cl will look like a second, or you can tell it will be as it is, means which is closer to the mirror that will come first. Simple things, which is closer to the mirror that will come first, front. And Cl was, suppose it was in just perpendicular 90 degree, then it will not change, it will look like same way. But this another was can say before this Cl 90 degree, it was just like the front, then that will come first. Okay, and again this both Cl and 1 En will come in the front, and which was the back, that will go to the back only. But both are you can say can't be non-superimposable, can't be superimposed. Then this is the two form. What is forming in the mirror, that is called labo, you can tell. Only direction, opposite direction is there. All things are same, opposite direction, just like left hand and right hand, correct? Or your you can say figure, if you are standing near the mirror, then your face, your original face and mirror face, what is the situation, correct? Same way, direction, only direction, opposite direction, that is the only difference. Then both form are called you can say optical isomer, dextro and labo. Then this I have given two example of these things. First example I have told about the cobalt En whole 3 and outside 3 plus, and another platinum Cl2 En whole 2 outside 2 plus. Okay, and here you should know that I told you these things two form. Now in second case P2 Cl2 En whole 2 plus, only the cis isomers show optical activity, only cis, okay, not the trans. Cis only show the optical activity. Question is asked, okay, PtCl2 En whole 2 outside 2 plus, only cis isomers show optical activity. Now this thing I told about the P2Cl2 En whole 2. Okay. Now I will tell about the when this is there, question is there. Okay. Actually, this type of question is asked. It comes under the complicated question, but that objective type question, multiple choice question, they can ask this. This question I am telling you, draw a structure of geometrical isomers of FeNH3 whole 2 Cn whole 4. Okay. FeNH3 whole 2 and this Cn whole 4. Outside 1 minus there. This is the anion. Central metal ion is ferrous. 2 ammonia is there, NH3 whole 2, and 4 cyanide is there, total 6. 4 cyanide, Cn whole 4. Outside 1 minus. Then you have to draw the structure of geometrical isomers. Means their spatial arrangement will be different. Then how can you write? How can you show? It is very easy to show. Correct? Always you remember I told you P2 platinum Cl2 and En whole 2 total 4. This type of complex ion will show only means Cis only show optical isomers Cis, Cis, not the trans. Only Cis will show optical isomer. You always keep in mind there are total 4 ligands, but here is 6 ligand, NH32 and Cn whole 4. Central metal ion is Fe, and you have to draw the structure of geometrical isomers. Geometrical isomers. Now I think easily you can write. Geometrical isomers means Cis also you can write Cis form and trans form. Then 2NH3 is there. Then very easily you can write in one isomer means in trans. In trans both NH2NH3 is there. Then both NH3 will be par. Ferrous is in the middle. One is above the ferrous, other is below the ferrous. A straight line like this way, straight way. Then now 4 cyanides are there. Then 2 you can write, 2 cyanides you can write left side and 2 right side. 2 left side, 2 right side. Then total 6 are over. 2NH3 and 4 Cn. But bond you make with C only, not with N. Cn everywhere, Cn. Then it will look like, if you will make it by point, it will look like this thing, circle. Okay, circle like that it will look like. Okay, but you have to not make a join it. So simply I am telling you, it is surrounding the Fe, iron. Now this is the trans. Then now after that Cis, already I told the meaning of Cis, that all ligand will be close, adjacent. When all are adjacent, only then you can tell this is the Cis. Then now in this situation, Cis situation, both NH3 will be close, adjacent to each other, and rest 4 Cn will be again close to each other. Means Cn, all 4 Cn are close. Okay, and but it will be just like a round. Okay, it will look like a round. Then all 4 Cn will be adjacent to each other, close, and both NH3 will be adjacent, close. Then this is the Cis form. Hence you can write like this way: geometrical structures of geometrical isomers of FeNH3 whole 2 Cn whole 4, outside 1 minus. Now one more question is there. That question is also important. Okay. Out of the, actually they have given two questions are there. Out of the following two coordination entities, which is a chiral? Chiral means optically active. Chiral means optically active. Always remember, wherever chiral will come, optically active. Both will be optically active. Chiral means optically active. Means it will be affected by molecules can rotate the light. Direction of light it can rotate. Then now first is a Csir. First complex is Csir, CrCl2 and OX whole 2, 3 minus. Outside 3 minus. Again I am telling you Csir. First question is Csir. Chromium, with chromium 2 chlorine is attached and 2 oxalate is there, OX whole 2. 2 oxalate is there. Oxalate is also didented. Didented means 2, this is there, they can donate, 2 atoms can donate the electron. Okay, 2 atoms can donate the electron. Then you have to find out that out of the second one is a trans chromium Cl2 OX whole 2. This one is Csir, other is trans. Then molecule is the same. Cr, chromium 2Cl2, oxalate 2 oxalates are there, 3 minus, and again trans is there, same molecule Cr, chromium Cl2, OX whole 2. Okay, 3 minus. Then you have to find out that which is a chiral optical active out of this, whether Csir or trans. Then now this Csir, already generally Csir will be the optical active. Okay, Csir. Then now if you will write the, but I can prove it only by these things, by mirror image. Only by mirror image you can understand if it is superimposing, then it is not the optical active. If they are not superimposing, then it is active, optically active, not superimposing. Then this can be proved only by mirror image. Okay. Then now both structure you have to write chromium Cl2 OX whole 2. Then same way representation, just like En, OX also you can write and you can join with platinum. 2 oxalate is there. Then 2 oxalate you can write, and both you can 2 bond both they will make. And same way what I told with En, and 2 Cl is there. 2 Cl bond is 2 chloride ion is attached to the platinum. And other trans means you know that molecules will be farthest opposite, 2 ligands will be opposite. Then now in trans, by just name itself is there, trans will be opposite, and Cl will be also opposite, trans, correct? Any one will be the opposite, whatever be. Suppose oxalate was opposite, then it's if you will see the image, mirror image, then there will be no difference. because both are trans. Then image will be also like that way only. One is in the front, other is in the back. Then figure will come like that way, one will be back, one will be front. Hence no change. Then in trans there is no change. Hence it can't be the optical active, because there is a mirror image, there is no change, as it is. Then means which was in the front and back you can't determine. There is no change in the position. In the mirror. Correct? In trans, because it is an opposite. In trans, opposite position will be opposite. Then diagram, if you see the mirror image, again it will look like same. Correct? No change at all. That's why trans will be not the optically active. But in siege, you will find that their position is different because they are adjacent. Then Cl is in the front and 2 oxalate is in the back side. Then it will look like that Cl will be, you will find a change here in direction. You will find here change. But in trans, it is not possible. That's why Sig means Sig chromium chloride, CrCl2OX whole 2, 3 minus is a chiral, means optically active. This is a important, very, very important question I have discussed. Now, linkage isomerism. Now I will continue isomerism, linkage. By the name itself, it is clear. Linkage isomerism. Linkage isomerism arises in a coordination compound containing ambidented ligand. A simple example is provided by complexes containing the thiocyanate ligand. Thiocyanate ligand, you know, that is the NCS 1 negative. Okay, because why it is this ambidented? Ambi means now through N also you can make the bond, through S also you can make the bond. That's why it is called ambidented ligand. Ambidented ligand means they can make bond with two atoms. Okay, only in the same ligand, they can make bond with two ligands. Their NCS, it can make bond with N also, and it can make bond with S also. Okay. Then this thiocyanate, which may bind through the nitrogen to give MNCS. M means metal. With metal it can join MNCS, or through sulfur to give MSCN. Now it is making, metal is making bond with S, and in the first case metal was making bond with N. Okay, that's why it is called ambidented. Then this is example of linkage isomerism. Then this I told you, and this one scientist was there, Jorgensen. He discovered such behavior in the complex CONH3 whole 3 NO2. This is in the bracket, square bracket outside Cl2 counter ion. Then actually this scientist Jorgensen actually just observed this behavior in this complex compound cobalt NH3 whole 3 NO2. Okay, NO2 in this ion outside is Cl2, which is obtained. How actually he got this? This complex ion is obtained as the red form, in which the nitrite ligand is bound through oxygen. When it was chromium was this cobalt, when cobalt was bonding with oxygen, NO2 was there. When it was bonding with oxygen, then its color was red and yellow, and as the yellow in which the nitrite ligand is bound through nitrogen. Okay, when it means by color he observed that bond is different. When oxygen was bonded with cobalt oxygen, then it was red form, and when it was bonding with nitrogen, cobalt was bonding with nitrogen, then it was yellow form, in which the nitrite ligand is bound through nitrogen. Okay, and this I told about the linkage isomerism example also I have told you. You remember the example in examination, this question can be asked. Now coordination isomerism. Coordination. This type of isomerism arises from the interchange of ligands between cationic and ionic entities of different metal ions present in a complex. Just it is only name itself is there, coordination. Then here there is a change in coordination, means cation and anion. In a complex compound, cation will be there, anion will be there. Cationic and anionic entities usually interchange of ligands. This type of isomerism arises from the interchange of ligands between the cationic and anionic entities of different metal ions present in a complex. As for example, cobalt NH3 whole 6, and this is the actually a cation, cobalt NH3 whole 6, and chromium cyanide whole 6, that is the anion. Then cation and anion, they will make coordination complex. Both are complex ion. One is cation, other is anion. Cobalt NH3 whole 6 is a cation, and chromium cyanide whole 6, that is the anion. Then now with the cobalt NH3 is attached, 6 NH3 is attached, and with chromium 6 cyanide is attached. Then now bring the cyanide to the cobalt and take NH3 to the chromium. Only ligand's position you are changing with metal. Now where cyanide was there, there you take NH3, and where NH3 was there, you bring cyanide. Ligand is the same number. Then what will happen? Then this is the new complex will be formed, cobalt CN whole 6, and now that will become chromium NH3 whole 6. Ligand interchanged. Then here you should understand that cobalt NH3 whole 6, chromium cyanide whole 6, in which the NH3 ligands are bound to cobalt 3+, and the CN 1 minus ligand, CN 1 minus cyanide ion ligands to chromium 3+. In its coordination isomer, what will happen? Chromium NH3 whole 6, cobalt CN whole 6. The NH3 ligands are bound to chromium 3+, and the cyanide ligands to the cobalt 3+. Okay. Then this is the example of coordination isomerism. Now come to the ionization. Ionization isomerism. This form of isomerism arises when the counter ion in complex salt is itself a potential ligand and can be displaced as a ligand, which can then become counter ion. Very easy. This form of isomerism, ionization isomerism, this form of isomerism arises when the counter ion in a complex salt is itself a potential ligand. Means counter ion can behave as a ligand. Counter ion in a complex salt is itself a potential ligand and can displace a ligand, which can then become a counter ion. An example is provided by the ionization of isomers. I am telling example: cobalt NH3 SO4, cobalt NH3 and inside the only square sulfate is there, and counter ion is bromide. Counter ion is bromide. Now what will happen? Now bromide will come inside, sulfate will go outside. Then it is interchange. Bromide came inside, sulfate went outside. Then now this cobalt NH3 SO4, that is in a bracket, outside is bromide ion, and CO NH3 bromide is now inside and sulfate is outside. Then this is the example of ionization isomerism. Means which was outside, they came inside, which was inside, that went outside. But these may be generally bromide, sulfate, chloride, iodide, like this way. Okay. Main cobalt NH3 is common in both. Hence there will be no benefit of changing. Both are same, cobalt NH3 in first also, in second also. But in first SO4 was joined with cobalt, but now in the new bromide came inside and sulfate went outside. Then both are the example of this is the example of ionization isomerism. Now one more, that is the solvate isomerism. Solvate isomerism. This form of isomerism is known as hydrate isomerism. Hydrate related to H2O. Hydrate isomerism. In case where water is involved as a solvent. Solvate, always solvate means it is related to water. Then this form of isomerism is known as hydrate isomerism, also called hydrate isomerism, in case where water is involved as a solvent. This is similar to ionization isomerism. Solvate isomers differ by whether or not a solvent molecule is directly bonded to the metal ion or merely present as free solvent molecules in the crystal lattice. Now this by example it will clear. Again I am telling you, this is actually matching with similar to ionization isomerism. Solvate isomers differ by whether or not a solvent molecule is directly bonded to the metal ion or merely present as free solvent molecules in the crystal lattice. Example I am telling you: aqua complex C chromium H2O whole 6. Chromium H2O whole 6 is in the square bracket, means complex ion, and outside Cl3 is there, counter ion. Its color is violet. And it's a solvate isomer. Now you can see that chromium H2O whole 5, in the beginning it was 6, now it became 5. One H2O went outside and one Cl entered. H2O whole 6 was only 6 ligand was there, all were H2O, and counter ion was chloride ion Cl3. Now what happened? Out of 6 H2O, one H2O went outside. To compensate this one H2O, one Cl came inside. In the bracket means with complex. Then outside it becomes one H2O and 2 Cl2, because one H2O went outside, replaced with counter ion. Then now it becomes Cl2, one H2O, Cl2, H2O, and inside CrH2O whole 5 and Cl. One Cl entered in the complex ion. Its color is grey-green. Its color is grey-green. Correct? Then now see two color. When it was H2O whole 6, it was violet. And now when one H2O went outside and its place one Cl came, now its color became grey-green. This is the best example of solvent isomerism. Now I am stopping only here. Next class I will start bonding in coordination compounds. Thank you.